Hello children, welcome back. Today's chapter Gravitation, chapter 8 for quick revision. The first topic is Kepler's laws. Johannes Kepler has developed three basic laws. First one is called Kepler's first law regarding planetary motion. The first law states about the shape of orbit, how planets revolve around Sun in what type of orbits. All planets revolve around Sun in elliptical orbits, keeping Sun as one of the foci of that ellipse. Planets revolve around Sun in elliptical orbit, keeping Sun as one of its foci. The second law is Kepler's second law, law of orbital aerial velocity, which is the direct consequence of conservation of angular momentum, law of areas, which states simply aerial velocity of the planet around Sun is a constant. Aerial velocity of planet around Sun is a constant, which can be also explained like this. The radius vector drawn from Sun to planet sweeps out equal areas in equal time intervals. The radius vector drawn from Sun to planet sweeps out equal areas in equal intervals of time, which is a direct outcome of conservation of angular momentum. Let us move to this topic. Let me show it on board. An ellipse has got two distinct axes. One is its longer diameter, which is called major axis. The other is called the shorter diameter, which is called minor axis. Center of ellipse is O. Ellipse has got two foci. Sun is at any one of the focus. Radius vector is drawn from Sun to planet. Suppose planet is at the tip of this arrowhead. That arrow represents position vector, instantaneous position vector of the planet. Now when the planet moves around Sun in elliptical orbit, both the length of this vector and direction of that position vector changes. So, as aerial velocity is a constant, when the planet is at farther places, it is to cover same area in same intervals of time. For that, it would be going slower, and then approaches it goes faster, then slower, then faster, again slower, faster, like this. The speed is not a constant. So the position vector turns through a very small angle when the planet moves from P to P dash. The planet moves from P to P dash. The planet describes a very small angle, maybe that angle d theta. The time interval in going from P to P dash is dt. And the angular speed omega is equal to d theta divided by dt. The distance travelled by the planet is ds. ds by dt is the speed of the planet. Speed, instantaneous speed over that small time interval. The instantaneous speed is ds by dt. The displacement vector can be drawn from P to P dash. Let that displacement vector be dr, vector dr. Then the instantaneous velocity vector be dr by dt. dr by dt is the velocity vector. The position vector has changed from vector r to r dash. And that area, this very small area mentioned in this picture, shaded. Let that area be dA, Kepler's second law. States that aerial velocity, which is dA by dt, is a constant. Aerial velocity is a constant. That area described can be written as dA is equal to half into base into height. So that dA by dt can be written as half into r into dr by dt. That is dA by dt is equal to half into r into instantaneous velocity. So this is equal to half rv can be multiplied and divided by m, where m is the mass of the planet. mvr happens to be the angular momentum of the planet around the sun with respect to sun reference. So mvr is L divided by 2m. In all planetary motions, planetary motion is motion under central field. Motion under central field, as there is no torque. There is only one force, gravitational force, which is acting along the line joining sun and planet. There is no torque. As there is no torque, angular momentum is conserved. That we have learned in chapter rotational dynamics. In the absence of external torque, angular momentum is a constant. So angular momentum of the planet around sun is a constant. M is already constant. L is a constant. That means dA by dt is a constant. Naturally, aerial velocity is equal to dA by dt equal to rv by 2 a constant. That is r proportional 1 by v, as dA by dt is a constant. rv graph is a rectangular hyperbola. r1 by r2 equals v2 by v1 in this same orbit itself. In the same orbit itself, same elliptical orbit, planet travels with dissimilar speeds. At farther place, going slow. Nearer place, going faster. At aphelion is the farther point. At aphelion goes slow, and at perihelion goes faster. Now dA by dt is a constant, that's why dA proportional to dt. All this very important for Kepler's laws. Okay. Then half into r into v. V can be written as r omega. So that d omega by dt can also be written as 1 by 2 into v can be written as r omega half r square omega, where omega can be written as d theta by dt, half r square d theta by dt. So dA can be written as half r square d theta. All that results are very important. It's very important, Kepler's second law. So Kepler's second law is the natural outcome of conservation of angular momentum, and it leads to consistency of aerial velocity. So a planet, radius vector, sweeps out equal areas in equal time intervals. That is Kepler's second law. Now the last law, third law, that is law of periods, states that square of time period of planet around sun is directly proportional to the cube of semi-major axis. Semi-major axis is the distance from center of that ellipse up to the point P, which is at the extremity of the major axis. That is half the length of the major axis. Major axis is 2a. So half the length of major axis is a. So t square proportional to a cube, that is t proportional a raised to 3 by 2. So t1 by t2 equals A1 by A2 all raised to 3 by 2. So these three laws, Kepler's first law, law of orbits. Second law, law of areas. Third law, law of periods. This build up the foundation of gravitation, chapter gravitation. The next topic what we have to go through is Newton's law of universal gravitation. Newton's law of universal gravitation states that we need two point masses m1 and m2 in space whose separation is small letter r. The force of attraction, mutual force, their interaction, F is equal to a proportionality constant into product of their masses and inversely proportional to square of the distance. Force proportional to m1, m2. Force proportional to 1 by r square also. Force proportional to m1, m2 and force proportional to 1 by r square. G is gravitational constant, its value is 6.6 into 10 to the power minus 11 unit Newton meter square divided by kilogram square. This force only depends on these two factors. Force does not depend on medium, surrounding medium, intervening medium. Force does not depend on temperature. Force does not depend on pressure. Does not depend on any other thing. Only force depends on product of their masses and distance. How it depends on distance? Distance inverse square law. F proportional to 1 by r square. In vector form, force on first body due to second body is equal to minus of G into m1 m2 divided by r12 square r12 cap, where r12 cap is the position vector. Minus sign shows that the force is attractive. Gravitational force is only attractive, always attractive. It is mutual gravitational force. And if these two masses are left freely, they are not held in space by some other forces. If they are not held in space by some other forces, that means if this gravitational force is not balanced with any other external agency forces, what would have happened? These two masses would have attracted and collided together. In the absence of any other forces, only gravitational interaction. What happens? That two masses cannot be in equilibrium. Each of those masses will collide, and that collision will take place at the center of mass of the system. We know we have learned in chapter rotational dynamics, center of mass of two particle system lies along the axis, lying joining the two, and that two close to the heavier one. If m1 is heavier, then center of mass is close to m1. So when left, no other forces, only gravitational force, m1 and m2 would move together, would accelerate, and that acceleration is variable because as the distance decreases, gravitational force between them increases. So acceleration also increases. So they will collide with very large acceleration, increased acceleration at the center of mass of the two particle system. Center of mass will be unaffected because center of mass is not acted upon by any external forces. The system moves, system of particles moves only because of internal forces. That's why state of center of mass would remain same. As center of mass was at rest before, now also center of mass would be at rest. Okay. If you have a massive shell, shell is of mass m, and radius of the shell is r. if you keep one more mass inside the shell, the force on small m from the part of capital M happens to be 0. This is also a consequence of this and can be called a shell theorem. So massive shell has only mass at the boundary. You have a small mass, a point mass inside, and the force on the point mass from the part of the shell would be 0. So the force on that point mass is 0 in the absence of any other bodies in the vicinity. Only these two masses, one is a distributed mass like a shell, other one is a point mass, and that point mass is inside anywhere, is not experiencing any force. That is shell theorem. But if there is any other mass outside, any other mass, a third mass outside, the third mass can interact with these masses. Outside mass can interact with this, both of these masses. But these two masses cannot interact. That's called shell theorem. That's a property of gravitational force. Now, we have to discuss acceleration due to gravity. That's to revise acceleration due to gravity. Value of G. Imagine Earth to be a uniform sphere of uniform density with radius r, center O. At surface, a point mass small m is kept, and the total mass of the planet, spherical planet, is m, which is uniform sphere. The gravitational force F is equal to G, capital M, small m, divided by r square. Then force per unit mass placed at the surface is equal to Gm by r square, which is nothing but the value of acceleration due to gravity at the surface. So the formula is Gm by r square at the surface. So value of acceleration due to gravity at surface is this. But at an altitude, G dash is equal to, it should be Gm by r plus h whole square. So you compare the values of acceleration due to gravities at surface and at a height above it. Height may be mentioned like this. Height is measured above surface. And if you raise that mass to this place, the value of acceleration due to gravity is G dash. At the surface, it is G. At that altitude, it is G dash. Then G dash by G is equal to R divided by R plus H whole square. Okay, that's why the value of G dash will be less than G. As you move from surface to altitude, the value of G decreases, G dash decreases. And when it is at a height of, by heard this result, 32 kilometer, the value of acceleration due to gravity decreased by a factor of 1%. So delta G by G is equal to minus 1%. That means at a height of 32 kilometer, the value of G decreased to 1% of its original value at surface. Let the value of G at surface be 100. Then the value at height 32 kilometer would have been 99. That means it has reduced by 100 minus 99, 1. Anyway, this all can be found by using this formula. You can substitute and get that previous question. So the factors over which value of G depends are mass of the planet, radius of the planet, height above the surface of the planet. As height above the surface of the planet increases, the value of G dash decreases. Also, if H is much less than radius of Earth, you can use another formula for variation of acceleration with the altitude. variation of acceleration with altitude if h is much less than r. G dash is equal to g into 1 minus 2h by r, and g dash minus g divided by g is equal to minus 2h divided by r. All these are previous questions. H much less than r, you can use an approximate formula. This is only an exact solution, an approximate formula, but the earlier one is an exact solution. This is only an approximate formula. So when you move from surface to altitude, value of acceleration due to gravity decreases. Value of g decreases when you move from surface to altitude. Okay, the factors over which g depends are mass of the planet, radius of the planet, height above the planet, surface. Once again, I am writing that formula Gm divided by r square. And also there is a well-known formula deduced from this one. Assuming Earth as a uniform sphere of volume 4 by 3 pi r cube and density rho. Volume into density will be mass. Substituting that here, you get another formula for G, 4 by 3 pi r rho g. 1 r only remains, r square cancels. So 4 by 3 pi r rho g. Here, g is found to be directly varying with radius. So when to use this equation? Before we said that g proportional to 1 by r square. Now we say that g proportional to r. So which comes true? Both are true depending on situations. If there are two planets having same masses, but their radii are different, then you use g proportional 1 by r square. Similarly, if there are two planets having same densities, same average densities, but their radii are different, then use the formula g proportional to. So what factors acceleration due to gravity depends? Then acceleration due to gravity varies with the depth also. When you move from surface to depth d, center O, and this total distance is r. Let this be the position at a depth d from surface. Depth is measured from surface. So rest of this distance is small r, that is equal to r minus d. Then at this depth, at the depth d, the formula for acceleration due to gravity, as you know, g into 1 minus d divided by r. So g dash minus g divided by g equal to minus d by r. That can be rearranged to write g dash equal to g into r minus d divided by r. Also g dash is equal to g by r into small r. See, this formula is very important, which says that g dash proportional to r. That is where r is equal to 0. G dash is equal to 0. So value of acceleration due to gravity at the center of the planet, where small r is 0. Because that point comes out to be at the center of the sphere. So that small r is 0, then g dash is also 0. So that is why an object feels weightlessness at the center of any spherical planet. And as you move away from center to surface, the value of g increases because g directly proportional to r. The variation of g with the radial distance from center to surface. Variation of g with radial distance measured from center to surface is linear. And that becomes maximum at the surface. But we have seen with altitude above surface of Earth, value of g decreases. So as you continuously move from center outward, then value of g increases at the first from 0 and it becomes maximum at the surface, then decreases. Center to surface increases linearly. Surface to outside decreases hyperbolically. Okay. If you plot a graph showing the variation of acceleration due to gravity, with radial distance on horizontal axis from center, G dash in y axis. You get a straight line. After that, you get a hyperbola. So up to surface the value of G increases, up to surface the value of G increases. So here the value is maximum, that is small letter g is equal to gm by r square. And here r less than r. Here g proportional to small r. Here r greater than r. G proportional to 1 by r square. And here at the position where small r equal to capital R, g dash is maximum. So this graph is also noted. Variation of acceleration due to gravity with rotation of Earth. Variation of acceleration due to gravity with rotation of Earth is also to be noted. Let this be the diameter. Let this be the axis. Axis of Earth. I am not showing the tilt. Angular speed omega. Earth is rotating with constant angular speed omega. A particle at equator. A particle at equator of mass m goes in a circular path acted upon by centrifugal force m omega square r. Then gravitational force directed towards center, that is mg. That's the weight of that point mass. One more force is the normal contact force acting outward, along outward normal. So the balancing of equations n plus m omega square r is equal to mg. So that n is equal to mg minus m omega square r. Okay. Then n can be written as mg dash. Mg dash is equal to mg minus m omega square r. So that g dash is equal to g minus omega square r. Cancelling m. So the acceleration due to gravity at equatorial region, at surface, any equatorial point on surface will be less than the value of g if it was not rotating. That is why if Earth suddenly stops rotating, the value of g would increase by this amount omega square. And also, you can see this equation. Here m constant, r constant, g constant. Here when omega varies, n can vary. If omega increases, normally that doesn't happen. If average angular speed of Earth increases, that r does not change, radius of Earth. M does not change, mass of that particle. G does not change, value of g at surface is a constant. But omega, average angular speed of Earth increases, then n would decrease because this is minus sign. So when average angular speed of Earth increases, n decreases and it becomes 0. When n becomes 0, that particle loses the contact from the surface. So that we can say mg is equal to m omega square r, m gets cancelled, omega equal to root of g by r. Thus time period equal to 2 pi root r by g, where r is the radius. G acceleration due to gravity, its approximate value is 1.4 hours. That means when Earth increases its speed so that its time period decreases, and when the time period becomes 1.4 hours, that means Earth rotates itself in 1.4 hours, close to 1.5 hour, very close, 1 hour 20 minutes something. Then 84.6 minutes. Then the person on equator will feel weightlessness. That's also an important question based on this. So variation of acceleration due to gravity with altitude, depth, rotation, variation with respect to size, shape, all that important. When size increases, radius increases, value of G decreases. It depends on shape also. The value of G at pole will be greater because polar radius is less. Equatorial radius is more. That's why value of G at equator is less normally. So variation of acceleration due to gravity is another important thing. Now intensity of gravitational field at any point due to any mass. Suppose you have a point mass. We have a point mass. Let that point mass be m. You have to find the intensity of that point mass at distance r, radial distance r. Then intensity E directed towards that point mass is defined as force per unit mass acting on that. That is G m divided by r squared. And if you have a point mass at this point, that intensity does not depend on that point mass. Intensity at that point P, intensity at the point P only depends on mass of the source and radial distance. It does not depend on mass of that particle at the point P. So mass of the particle is at the point is small m. Intensity at that point P, it is not affected by that small m. It only depends on mass of that source. That's intensity. Gm divided by r square. Now gravitational potential and gravitational potential energy. You have a point mass, capital M, at radial distance. The gravitational potential at the point P is defined as negative of Gm divided by r. Force is always attractive, that's why gravitational potential is negative. Similarly, gravitational potential of a spherical planet maybe a distributed mass for any exterior point, distant r greater than r, you can use same formula. But that distributed mass, distributed over a volume, you can assume that entire mass is concentrated at the center so that that radial distance is measured from center to that point. It's not from surface. All radial distances are to be measured from center of gravity, where entire mass is supposed to be concentrated. Because gravitational force is a central force. Now gravitational potential energy of two particle system, each of masses m1 and m2. Draw a line joining the two. Distance is r. Gravitational potential energy is minus G m1 m2 divided by r12. Minus G m1 m2 by r12. Same can be applied to four masses of any number of masses by using principle of superposition. If three masses are there, all identical, for simplicity I am using identical masses, distances are A. Let this form an equilateral triangle, all sides are equal. Potential energy of any one pair minus G m square by A minus G m1 m2 by r minus G m square by A. But three such pairs are there, so multiply by 3. So total potential energy you can add like this. This principle is called the principle of superposition. So potential energy of system of particles. So we have discussed force, intensity, potential and potential energy. Okay, also you can use the force is a conservative force, so force can be derived directly from potential energy. F is equal to minus du by dr. Any conservative force is derived from potential energy by this formula, F is equal to minus du by dr. Minus sign shows that the direction of conservative force is along the decrease in potential energy. Now we move on to an entirely different topic called escape velocity. Escape velocity. Escape velocity of an object projected from surface of planet is the minimum velocity with which that object is to be projected so that that body escapes from the gravitational field of that planet. Suppose our planet, a spherical planet, radius r, mass m, an object of mass mol m is given an upward velocity. If that velocity is the escape velocity, the kinetic energy of that object should be numerically equal to the potential energy of that object at the surface minus gmm divided by r for just escaping. So half m v square equal to gmm by r. Potential energy numerically. So you can neglect this sign. Numerical potential energy equal to kinetic energy. M gets cancelled, you get VE equals root of 2 gm divided by r. This can also be written as root of 2 gr. This can also be written as root of 8 by 3 pi r square rho g by using the formula for small g in terms of density. Small g in terms of density already we have discussed. 4 by 3 pi r rho g. So it becomes 8 by 3 pi r square rho g. So see, escape velocity depends on radius in different occasions differently. If two planets are having same values of acceleration due to gravity at surface, v proportional to root r. If two planets are there having same masses but different radii, v proportional to 1 by root r. Two planets are having different average densities, but their radii are different. Then use v proportional to root r square. That means root r square means that square cancels. Then v proportional to r. So v depends with r differently in different situations. So when an object is projected with escape kinetic energy naturally equals gmm by r. Object is projected with escape velocity. Kinetic energy is numerically equal to the potential energy. Okay, if you project a body from surface with its kinetic energy equal to potential energy at the surface, it just escapes. Okay, is that the only possibility to escape? No. If that kinetic energy is more than the numerical value of potential energy, also it can escape. But that body projected from surface does not escape if its kinetic energy is less than the numerical value of potential energy. That implies if an object is projected with a kinetic energy equal to the numerical value of potential energy at that place, its total mechanical energy would be 0. So that from conservation of mechanical energy, as in these situations we neglect the non-conservative forces like frictional forces and all, we can say that mechanical energy is to be conserved, for which 0 total mechanical energy is maintained throughout the motion. So when an object is projected with escape velocity, its total mechanical energy at the point of projection is 0. On the onward journey, during the onward journey also, its total mechanical energy becomes 0, but its kinetic energy reduces. Kinetic energy reduces as it go. And at highest position, where it just escapes, kinetic energy becomes just 0. Potential energy, but increases as it goes from surface to that point, where at the point where it escapes, potential energy becomes again 0. Potential energy increased and became 0. Kinetic energy decreased and became 0. Why potential energy increased value has 0? Because initially potential energy was more negative. Now it became 0. If furthermore it moves upward, potential energy becomes positive. Till then, potential energy was negative. Very bound systems have negative potential energy. So that's all about escape velocity. Now satellites. Last topic of the chapter. Satellite. First we discuss orbit speed of a satellite. Orbit speed resembles the formula for escape speed. Orbit speed is equal to square root of Gm divided by small letter r, where small letter r is equal to r plus h. That is, orbit speed is equal to square root of Gm by r plus h. Okay, the changes can be made as we have done before. Also, we depends on mass of the planet, we depends on radius of the planet, we depends on height above the planet, but we does not depend on mass of the object. As escape velocity also does not depend on mass of the object. Escape velocity does not depend on angle of projection. Okay, but escape velocity and orbit velocity depends on the height above surface. Okay, for close orbit, it's very important. Close orbit satellite, orbit speed, minimum orbit, that is equal to root of Gm by r. We can neglect h. H is much less than r. That's why h is neglected. So root Gm by r. Then escape velocity can be root 2 times the orbit velocity. Escape velocity can be mentioned as root 2 times the orbit velocity. Escape velocity divided by orbit velocity is equal to root 2. Escape velocity divided by orbit velocity equal to root 2. Root 2 means that 1.414. That is, escape velocity is 41.4% higher than orbit velocity. It's very important. So orbit velocity proportional to 1 by root r. So different orbits, the speed would be different. As the orbit radius increases, satellite moves on to a higher orbit. Okay, greater altitude orbit, then its speed decreases. R inverse 1 by root r. Now, orbit time period. Time period of satellite. Time period of satellite is equal to distance traveled divided by speed. So time period is equal to 2 pi root of r cube divided by Gm on substitution. That is T proportional to r raised to 3 by 2. As in Kepler's law, we get the similar result, T square proportional to r cube. It is true for the circular orbits also. Satellite can have circular orbit and also it can have elliptical orbits. It's very important. When a satellite can move in circular orbit, if the satellite is projected, the projection speed or the speed of the satellite is exactly equal to root Gm by r. If the speed of the satellite is exactly equal to root Gm by r, that can go in circular orbit. If that speed is slightly more or that speed is slightly less, it can go in elliptical orbit. So here time period formula, this may be for elliptical orbit or circular orbit. Both it is valid, and we have written here for circular orbit. That's why we could write perimeter as 2 pi r. So time period. Then energy of satellite. Kinetic energy of satellite. That topic is also important for revision. We are doing a quick revision only. Kinetic energy K is equal to half m into orbit velocity square. Orbit velocity is Gm divided by r for close orbit. I am only writing for close orbit. Okay, if not close orbit, you can use r plus h in place of r. So Gmm by 2r. Now potential energy PE, potential energy of the close orbit satellite, U is equal to minus Gm1 m2 divided by r. Now total energy of close orbit satellite minus Gmm by r plus G mm divided by 2R. That implies you get minus G mm divided by 2R, because it is minus 1 plus 1 by 2 becomes minus 1 by 2. So the triangular relationships between total kinetic and potential can be expressed as, what is the triangular relation between the three? Kinetic energy can be written. Kinetic energy can be written numerically equal to total energy. That is kinetic energy negative of total energy. Now potential energy equal to 2 times total energy. Potential energy equal to 2 times total energy. Both negative. Now kinetic energy equal to minus of potential energy divided by 2. See, kinetic energy equal to minus of potential energy divided by 2. This is potential energy. Minus of potential energy by 2 becomes kinetic energy. Or potential energy equal to minus of 2 times kinetic energy. So these triangular relationships also to be noted. Different types of satellites mentioned in our textbook. First one is geostationary satellite. Geostationary satellites follow near circular orbits at a height 36,500 km above surface of Earth with time period 24 hours, used for communication purposes mainly. Polar satellites, other type, altitude nearly 500 to 800 km and time period is very close to 100 minutes. Time period is very close to 1.5 hours. That's why it takes only very less time to rotate around Earth in one circle. It moves in polar orbits, but geostationary satellites move in equatorial orbit. Geostationary satellites, why called geostationary? The orbit is called parking orbit, because that satellites appear to be remaining at rest as seen from a given place on surface of Earth. Moon is a geostationary natural satellite of Earth. Now, polar satellites are altitude much less, that's why it can move around Earth many times a day itself. But so close to surface of Earth, it can be used for getting high resolution pictures of Earth. The last topic to be revised is weightlessness in a satellite. A person in a satellite is always in the state of weightlessness because the person inside the satellite is at a state of freely falling. Suppose you are falling from a taller building or mountain freely. Never practice it. Okay, then a person in satellite has that feeling. It is because the entire force of gravitational attraction from the part of the planet to the person inside the satellite is completely utilized as centripetal force. And the responsibility of that gravitational force is only to make that person inside satellite also moving in circular orbit like satellite. That's why no component of the force of gravitational attraction between that person and Earth is used for pressing the platform of the satellite over which the person is there. So entire force of gravitational attraction is used as centripetal force, that is used for counteracting the centrifugal force. That's why the person inside satellite feels weightlessness. Okay. We have almost completed the chapter. We have done this as a quick revision. Okay, I have tried to explain almost all the points clearly. You can watch the video and we'll be meeting again with the next chapter soon. Thank you.